Today we're going to be looking at Descartes' rule of signs. So I've got the rule written down here. And what it says is, let f of x define a polynomial function with real coefficients in a non-zero constant term with terms in descending powers of x. Okay, then part A says the number of positive real zeros of f either equals the number of variations in sign occurring in the coefficients of f of x, or is less than the number of variations by a positive even integer. Part B says the number of negative real zeros of f either equals the number of variations in sign occurring in coefficients of f evaluated at negative x, or is less than that number by a positive even integer. Okay, Descartes' rule of signs does not read very well. So we're going to, it's clear as mud, isn't it? So we're going to clear this up with some examples. So I've got a polynomial function here, f. It's got real coefficients. It's got a non-zero constant term. And the terms are in descending order with the powers of x. Okay, so I've met all the conditions. And so let's look at answering part A. So part A would be how many positive real zeros does f have? Okay, so let me just put that clear as mud rule back up here. The number of positive real zeros of f either equals the number of variations in sign. Well, what the heck does that mean? We're going to count up the number of times going from left to right that the sign changes. Okay, so I'm going to get a different colored pen. And we're going to start here. We're going to go left to right. So we have positive 2 times x to the 8th. And we go from positive to negative. That's a change in sign. So I'm going to count that as my first change. So I'm going to put a 1 there. Then I go from negative to positive. That's another change in sign or variation in sign. So that's my second change in sign. Now, going from here to here, I go from positive to positive. So there is no change there. So I'm not going to count it. When I go from here to here, I go from positive to negative. That's another change of sign, and it is my third change of sign. I keep going, negative to positive. That's another change in sign, and that brings me up to 4 changes or variations in sign. And then finally, I go from positive to positive. That is no change. So when I went through from left to right, there were 4 changes in sign, or as that rule loves to say, 4 variations. But just think changes in sign. Okay, so what does that mean? Well, it means f will have either 4 positive real zeros, or, let me put the rule back up here. So it either equals the number of changes in sign, which was 4, or is less than that number of changes by a positive even integer. You keep subtracting 2 from the number of changes in sign. So f will either have 4 positive real zeros, or 4 minus 2 is 2 positive real zeros, or it won't have any because 2 minus 2 is 0. So f will either have 4 or 2 or no positive real zeros. Okay, so that's part A of Descartes' rule of signs. So I'm going to come back and do part B later. Let's just stay with part A until we're sure about that we're confident that we can do these for part A. So here's another polynomial. It's got real coefficients and it has a non-zero constant term, and my powers of x are in descending order, so it meets the qualifications. Just focus that a bit. Okay, again, let's look at part A. How many positive real zeros does this polynomial, and this polynomial is called g, does this polynomial function g have? And let's use Descartes' rule of signs. So I'm going to go from left to right, and I'm going to count up the number of changes, or as they like to say, variations in the sign. So I'm starting with a positive, and I go from positive to positive, no change. I pick up positive to negative. That is a change. That's my first change. Negative to positive, that's another change in sign. That's my second change. Positive to positive, no change. And positive to negative, that's a change in sign, and it's my third change in sign. So how many positive real zeros does G have? Well, we had 3 variations or changes in sign. And so that means that my polynomial G will have either 3 positive zeros or you keep subtracting 2, and 3 minus 2 is 1. And then I stop there, because if I subtract 2 from 1, it doesn't make sense to say it'll have -1 positive real zeros. And like with the, I should have put a half there. Like with this one before, it had 4 changes in sign, so it's going to have either 4 positive real zeros, 2 positive real zeros, or none. And so we stop when we get to none, because it doesn't make sense to say, oh, it'll have -2. So we stop subtracting 2 until you get down to the number 0 or to the number 1. So in this case, G will have either 3 positive real zeros or just 1 positive real zero. Okay. Are we starting to get the hang of it? Let's do one more about this guy. So now my polynomial function is h. It's got real coefficients. Its constant term is non-zero, and my powers of x are in descending order. So how many positive real zeros will h have? Well, we do Descartes' rule of signs, and we count up the changes or the variation in sign, going from left to right. So I go from positive to positive, no change. Positive to positive, no change. Again, no change. No change. I have gone all the way through, and there was no change in sign. There have been no changes or variation in sign. And that means that H has no positive real zeros. So when you're using the rational zeros theorem to make your list of possible rational zeros, you know how you get your list with plus and minus? Well, you can eliminate all the positive ones because by Descartes' rule of signs, we have said definitively this polynomial h will have no positive real zeros. So that's where Descartes' rule of signs comes in handy. On the previous ones, we didn't get much information. So here, well, there's either going to be 4 positive real zeros, 2 positive real zeros, or none. That's not much of a help, is it? Now, we've got a little bit of a help here because we concluded there would be 3 positive real zeros or 1 positive real zeros. We definitely know there will be at least 1. So you know to look in your list, if you've checked, definitely check for the positive ones. And if you find 2 positive real zeros, you know there's going to be 1 more. So that is helpful. And then here, this would be the most helpful because we can eliminate any possibilities in our rational zeros theorem list of the positive ones. And now let's get on to the part B. Now the part B is the more challenging part. So if I was going to answer part B using Descartes, part B would be how many negative real zeros does f have? Let's see if I can get a pen that works better. How many negative real zeros does f have? Well, let's put the rule back up here. The number of negative real zeros of f either equals the number of variations in sign occurring in the coefficients of f of negative x, or is less than that number by a positive even integer. We've got to write the formula for f of negative x. So we are not using this formula to answer part B. We have to have the formula for f of negative x. So I'm going to find a better pen, hopefully, and now, how do you write the formula for that? Well, this is the long way. So I'm going to show you the long way, then I'm going to show you the shortcut. So if I want to write the formula for f of negative x, everywhere there's an x in here, I'm going to replace it with negative x in parentheses. Okay, but I cannot apply Descartes' rule of signs yet. I can't start counting sign changes until I get this written without parentheses. Now, the exponent, the power is even. What happens to the negative sign if the power is even? It goes away. The power here is odd. What happens to this negative sign inside the parentheses if the exponent is odd? We keep it. And so I'm going to have 2 negative symbols and they will cancel each other out. What happens to the negative sign inside here? The exponent is even, so it goes away. What happens to the negative sign inside here? The exponent is odd. It stays. What happens to the negative sign inside here? The exponent is even. It goes away. So I will have this negative symbol, but that one goes away. What happens to the negative sign inside here? The exponent is even, it goes away. Now, it's only when I have it written without parentheses that I can do the test. Now, I told you I would show you a shortcut. So here's the shortcut. Let me get a blank sheet of paper. Okay, so I'm going to do it again, but this time I'm going to do it super fast. And if you can remember this rule. So when you have a polynomial function and you want to evaluate f of negative x, if the exponent is even, nothing changes. If the exponent is odd, the sign out the front will change. So let's do it the fast way. The exponent is even, nothing changes. The exponent is odd, the sign will change. The exponent is even, nothing changes. The exponent is odd, the sign will change. The exponent is even, nothing changes. The exponent is even, nothing changes. And of course that will stay the same. And let's see if I got the same answer. I sure did. And wasn't that a lot quicker? Okay. So, I'll take this sheet off. So we're here. Now let's do the test. Let's count how many variations in sign, how many changes of sign we have. I go from positive to positive, no change. Positive to positive, no change. Positive to negative, that is a change, and that's my first change. Negative to negative, no change. Negative to positive, that is a change, and it's my second change. Positive to positive, no change. So, throughout this, the polynomial function f of negative x had two variations or changes in sign. And so by Descartes' rule of signs, that means that the polynomial f, the original f, will have either two negative real zeros or, well, we keep subtracting 2, and 2 minus 2 is 0. So, or no negative real zeros. Okay, so here was our result for how many positive real zeros f would have using Descartes' rule of sign. This is our result for how many negative real zeros f would have using Descartes' rule of signs. Okay, we're done with f. Let's go back to g. So let's answer part B. How many negative real zeros does G have? Okay, I've got to get the formula for G of negative x and then count the number of changes in sign. So let's do it the super duper fast way. The power is odd. The sign will change. The power is even. Everything stays the same. The power is odd, so this sign will change. The power is even, so everything stays the same. The power here is odd because x by itself is the same as x to the first power. So the power here is odd. The sign will change. And the constant stays the same. The constant is constant. Now I have the formula for g of negative x. Now I can do the test to see how many negative real zeros g will have. So I take my different colored pen. I have negative going to positive. That is a change. That's my first change. Positive to positive, no change. Positive to positive, no change. Positive to negative, that is a change. It's my second change. And negative to negative, no change. So throughout that, g of negative x has two changes or variations in sign. And so what that means is the original polynomial g, therefore, g will have either two negative real zeros or 2 minus 2 is 0, so or no negative real zeros. So by Descartes' rule of signs, this is what I conclude for how many positive real zeros g will have. This is what I conclude about how many negative real zeros g will have. And let's finish up with the last one. So now we're back with our polynomial h. So part B, how many negative real zeros will h have? Well, we have to get the formula for h evaluated at negative x. And let's use the fast way. This exponent is odd, so the sign changes. This exponent is even, so everything stays the same. This exponent is odd, so the sign changes. This exponent is even, so everything stays the same. And the constant is constant. It will stay the same. Now I can do my test. I'm going to count up the number of variations or changes in sign. I go from negative to positive. That is a change. That's my first change. Positive to negative, that's another change in sign. That's my second change. Negative to positive, that's my third change in sign. And positive to positive, no change. So when I went through, I had a total of 3 changes in sign. So h evaluated at negative x has 3 changes in sign. So that means my original polynomial h, therefore, h has either 3 negative real zeros or 3 minus 2 is 1 or exactly 1 negative real zero. So using Descartes' rule of signs, I had a very powerful result here in part A. It will have no positive real zeros. And I get a little bit of help in part B. I know that there exists at least 1 negative real zero. So at least I know that it does have at least 1 negative real zero. Okay. And that ends this lecture on Descartes' rule of signs.